Good morning, everyone. Today, I'm going to present a video lecture on one important reaction. So that reaction is Beckmann rearrangement. So what is Beckmann rearrangement? What is a reaction and mechanism to understand this Beckmann rearrangement is our objective of today's session. Okay, so we'll try to understand what is Beckmann rearrangement first. So when ketoxines undergoes rearrangement, in the presence of sulfuric acid, it forms N-substituted amides. Okay, so this is known as Beckmann rearrangement. So in simple words, if you want to understand, Beckmann rearrangement is nothing but when ketoxines undergoes rearrangement in the presence of sulfuric acid, it forms N-substituted amides. Okay, so if you see the reaction for this, so this is your oxime functional group, and this is CH3. So this is called as methyl phenyl ketoxine. So this I'm going to react with concentrated sulfuric acid. So you're going to get N-substituted amide. So this is N-phenyl acetamide. Okay, so methyl phenyl ketoxines, when reacted with concentrated sulfuric acid, you are going to get N-phenyl acetamide. So when ketoxines are converted into N-substituted amides in the presence of sulfuric acid, you can call it as Beckmann rearrangement. Okay, so coming to the mechanism of this reaction. So the first step is the protonation of hydroxyl group of ketoxide. So you know protonation is nothing but addition of proton or hydrogen atom. So I'm going to write that methyl phenyl ketoxine structure here once again. So you know oxygen will have two lone pair of electrons. Thus I'm going to react with sulfuric acid. So when sulfuric acid undergoes dissociation process, you will get H plus and HSO4 minus. Okay, so this H plus can be stabilized by using this oxygen, which have two lone pair of electrons. So oxygen is ready to donate its lone pair of electrons for this H plus ion. Therefore, a new sigma bond will be formed between oxygen and hydrogen to form OH. So I'll write the structure here. and here you will get OH2. Okay, why? Because this extra hydrogen atom is coming from this H plus, where oxygen will donate one lone pair of electron to hydrogen atom. Therefore, this hydrogen atom will migrate towards OH to form OH2. Okay, so coming to the second step, I'll erase this statement and the general reaction also. Right. So coming to the step number 2, migration of phenyl group and elimination of water. So elimination of water is nothing but your dehydration reaction. Okay. So I'm going to write the intermediate compound, what you got in step number 1, once again here. OH2, and here, as oxygen donated one lone pair of electron for hydrogen, oxygen will get only one lone pair of electron here with a positive charge, right? So the same thing I'm going to write here also. Right. Now, what is the problem with oxygen? Oxygen is having only one lone pair of electron, but when oxygen will have two lone pair of electrons, okay, then only oxygen will be stable and we can remove a water molecule very easily. Okay, so what will happen is I will break the bond between nitrogen and oxygen here. So as oxygen is more electronegative, the electrons which are present in the sigma bond will migrate towards oxygen. Therefore, oxygen will get another lone pair of electron here. So this entire water molecule will be eliminated out. Okay, this H2O will be eliminated out in the form of a water molecule. So this reaction, you can call it as dehydration. Okay, so when these electrons are migrated towards oxygen atom, oxygen is stabilized and water is removed as a byproduct. Then what happens to this nitrogen here? Nitrogen will get positive charge or electron deficiency. So to stabilize this positive charge, okay, the phenyl group will migrate towards nitrogen atom. You know, phenyl group is a very powerful nucleophile. So it can donate the electrons very easily. Okay, so this phenyl group will shift towards your nitrogen atom here. Okay, so as soon as the phenyl group shifts towards nitrogen atom, okay, so this carbon will get electron deficiency. Okay, now I'll write the structure here. You will get the same CH3 single bond carbon. Here carbon will get positive charge. Why? Because previously this carbon was attached with phenyl ring. Okay, so now this phenyl ring has been migrated towards the positively charged carbon. Therefore, this carbon will have a positive charge, followed by double bond N. And here you can attach your phenyl ring. So this is the compound and this is your carbocation. So carbon which is having a positive charge, you can call it as a carbocation. Okay, so in the next step, we are going to stabilize this carbocation. Okay, that is step number 3. nucleophilic attack on carbocation. Okay, so I'm going to erase this. So I'll write the same structure once again here. CH3, carbon with a positive charge, double bond, nitrogen, and this nitrogen is attached with a phenyl ring. So what I'll do is I will use this water molecule which is liberated in step number 2. Okay, so water. So here oxygen will have 2 lone pair of electrons. So when these lone pair of electrons are shifted towards this positively charged carbon, this entire water molecule will add on this particular carbon. Okay, so you will get a structure CH3, C, and here you will get a water molecule H2O, but oxygen will have only 1 lone pair of electron. You can designate it by a positive charge followed by nitrogen with a phenyl ring. Okay, it is simply an addition reaction where water molecule has been added on this positively charged carbon, because as carbon is having positive charge, oxygen will donate its lone pair of electron to this positively charged carbon. Therefore, a new sigma bond. So this is a new sigma bond which is formed between the carbon and oxygen. So this is how water has been added on this particular carbon. So sometimes we can call this reaction as hydration. Hydration is nothing but addition of water molecule. Okay, so coming to the last step of this Beckmann rearrangement, step number 4. So step number 4 is deprotonation. And formation of N-phenyl acetamide, which is your final product. Okay, now I'm going to write the same structure what you got in step number 3 here once again. CH3, C. I'm writing this water molecule in this way to understand the mechanism. Okay. So here oxygen will have positive charge because already it is having only 1 lone pair of electron. Right. So first what we need to do is we need to stabilize the positive charge on the oxygen atom. Okay. So if you compare the electronegativity between oxygen and hydrogen, oxygen is more electronegative. So the electrons will be shifted towards oxygen atom and hydrogen will become positive charge. So this hydrogen will be eliminated out. So this is called as deprotonation reaction. Okay, so in the next step, you are going to get CH3, double bond, okay. Now, this is nothing but your enol form of N-phenyl estamide. So what do you mean by enol? En refers to the presence of a double bond. OL refers to the presence of the OH group here. Okay, so this enol form has the capability to convert into a keto form. That is, keto-enol tautomerisms can be formed. Okay, so I will show you how to write the keto form of N-phenyl estamide. So already the product has been formed, that is enol form of N-phenyl estamide is already formed here, but this enol form readily undergoes tautomerism to convert into a keto form. Now you can look at here. This can be converted into, so you compare the electronegativities between carbon and nitrogen. So what happens here? The pi electrons will migrate towards nitrogen atom. So initially nitrogen will hit one lone pair of electron. If these electrons are also migrated towards nitrogen, nitrogen will get two lone pair of electrons. Okay. At the same time, when this pi bond migrates towards your nitrogen, here you will get a positive charge. Carbon will get positive charge. Now to stabilize this positive charge, okay, I'm going to break. So here oxygen will have two lone pair of electrons. If I break the bond between this oxygen and hydrogen, hydrogen will get positive charge. Okay, so oxygen will now get extra lone pair of electron. So this extra lone pair of electron, it will donate for carbon. So carbon will form a double bond with oxygen. Okay, and here nitrogen is having two lone pair of electrons. So this extra lone pair of electron, it will donate for hydrogen. Therefore, nitrogen will form another bond with hydrogen atom. So you'll get CH3. Here you will get C double bond O. Okay, why? Because oxygen is having one extra lone pair of electron. It will donate for positively charged carbon. So this carbon can form a double bond. And here you will get a single bond because one pi bond has been migrated towards nitrogen, which is more electronegative. Okay, actually nitrogen will have only one lone pair of electron. So when these pi bond is migrated towards nitrogen, it will get another extra lone pair of electron. Okay, so nitrogen, so this extra lone pair of electron, it will donate for this H plus to form NH, followed by the benzene phenyl ring. Okay, so this is the keto form of N-phenyl estamide. Okay, so this is a mechanism for your Beckmann rearrangement process. Thank you.